Video, I'm going to walk you through another example from chapter 2 on recursively defined data type and how to recursively process information or how to define a interface using procedures to such data types. So I'm gonna go to chapter 2, examples, and then scroll down. So the example we have looked at before is this environment interface. So we look at the data structure representation and the procedural representation. So if we can come up with a interface definition, then we can separate the interface from the implementation. So our data type, in this case environment, behaves the same to the client code regardless of how it's implemented, right? So we're going to look at another example, that is the lambda calculus expression, which is a reductively defined data type, and we're going to build an interface for it so that we can our code can stay simpler, and we can decouple the interface from the implementation. So I'm going to go back to chapter 1. I'm going to review the lambda calculus syntax. So this is the grammar, the syntax for lambda calculus expression. So given an expression like this in scheme, so if it's a lambda calculus expression, it's going to be one of the three kinds. So it can be a variable, can be an identifier, just a variable, a name of something, or it can be a lambda expression that this looks like a list. Okay, in fact, if you type this in a scheme, this is treated as a list. But then the first element is the keyword lambda, and then the second can be an identifier, and then the body is any lambda calculus expression. So this is the concrete syntax, right? This is treated as data because we're writing programs that are interpreters. They can read source code as data and then figure out its meaning. And then the third kind is just in parentheses as a list, any lambda expression followed by another lambda calculus expression. Right, so we're going to deal with this kind of data and try to answer the question whether a variable occurs free in this expression or not using the logic we have studied before. Okay, so in the past implementation, we had this car of Curder, which is hard to read, right? It's hard to, it's not as clean as we want. So now we're gonna build a interface to this data type so our program can look simpler, easier to understand. So we're gonna build a set of procedures. We have three constructors. So we're going to have a procedure that takes a variable and turn into a lambda calculus expression representation. And then we have lambda expression. So it takes a variable, a lambda calculus expression, and then it turns into a lambda calculus expression. So those are constructors because we construct, we build these three kinds of variants for our data type, right? So there's only three kinds. And then we have predicate that test whether this, what we have is one of these three types, right? So they all take lambda calculus expression, this object that we construct, and returns a Boolean, true or false. And then we have extractors. We have ways to take them apart, right? If it's a variable expression, we can take a variable expression representation and then return the symbol for the variable. If it's a lambda expression, we can get its bound variable, which is the formal parameter, or the body of the expression as a lambda calculus expression. And then if it's a complicated expression, we can take we can get the first element, which is the operator, and then the second element, which is operand, right? So this is the interface of those procedures. So now, before we look at concrete implementation, now we can define a occurs free procedure more easily by making use of these procedures, because they hide the details from us, right? They are interfaced to this recursive data type called lambda calculus expression, or representation of lambda calculus expression. So recursive takes a symbol and lambda calculus expression, okay, this kind of data we're constructing, and then give us a Boolean value answer, true or false, right? So here I'm gonna use count to test whether what we get, what kind of object it is, what types of object we have. So if it's a variable expression, then we extract the variable from the variable expression and then compare this to search variable, and if it's true we return true, if it's false we return false, right, using the recursive logic. If it's a lambda expression, we're gonna extract the bound variable, the body of the expression, and then we're gonna so we compare the bound variable with the search variable. If they're the same, then it's not, so we return, if this is true, not is false, and the whole thing is false, so it's not free, so return false. Otherwise we're going to recursively call occur free using the search variable and the body of the lambda expression, right? So this is the logic, the same logic, except we used our interface procedures. So otherwise we're going to treat the operator and operands as lambda calculus expressions, right? So we're going to recursively search and apply this procedure, and then we take the result and use OR, right? Because the variable occurs free in the whole expression if it's either it's free in the operator or it's free in the operand. Okay, so now so if we add this, we can define those interface procedures, then we can test it and it give us the correct answer. So it's the same test case, right? From the client perspective, this occur free behaves the same, but the implementation is now changed, right? So here is the answer. How do we implement those interface procedures, right? Variable expression, this is a constructor, it's a function, a procedure. Given a variable, it's just turned into a variable. And if it's lambda expression, we're going to use a tagged list, right? So this is a list, we build a list with a tag, but then inside we're going to have figure out a way to to store the two elements, the two fields, the bound variable in the list by itself and the body, right? And then similarly, if it's app expression, we're gonna just create a list with the two expressions, to the operator and operands in the list. Okay, so if it's a variable expression, okay, so this is the predicates, right? So we, based on how we implement the constructor, we implement the predicates so we can answer the question correctly, right? If expression, the representation of expression is a symbol, then it must be a variable expression, so we return true. Otherwise we return false. A lambda, we'll look at the it has to be a pair, and then the first element has to be lambda, right? We look for this tag in our list. If it's app, to test whether what we have is an app representation of an app expression, we make sure it's a pair, it's a list. A list is a pair. A list start with a pair, and then the second element is also a pair. It's how we store the bound variable as in a list, and then the third. Hold on. So yeah, the first is the whole thing is a pair, and then the courter, which is the rest, is a list, right? And then the courter of the courter is a null. So if all of them is true, then we call it, we return true, so it's absolute. So this is not bulletproof, but it works for now. So okay, and then we have the extractors. So we can give given a var expression constructed using one of the constructors, we can return the variable, and then similarly we can take a part of a expression, a lambda expression created using the constructor. No, the constructor is here, and then we can take it apart. It's a list of lists, and then we use the car of the coder, and then so on and so forth, right? So now I'm gonna copy this code to my editor. Okay, so looks like my so my editor has died. Kill it. Okay, so I'm gonna open it again. Okay, so I'm gonna use UPL language. So paste this, but then I'm gonna add those constructors, those interface procedures, right, from the second block, from here. I'm gonna add it at the beginning. Okay, so now I'll run. Okay, so everything works. So let's look at this. Okay, so I'm gonna test those constructors. So this construct a lambda calculus expression according to our constructor, and then it's just a symbol by itself, right? For lambda calculus expression, it just gives us a list of lists, right? A tag list with something like this. And then let's look at another example. So what is this? So this is a app expression. So this is constructor. We have to provide the operator and operand, right? So they have to be valid lambda calculus expression representation as well. So we use the constructor to construct them, and then this give us the internal representation of app expression. So we actually call it abstract syntax later on, but this is given. So this is a constructor that gives us this kind of representation, and then our extractor, our other. Let me do this. And so I'm gonna use this. So let's see. We construct the app expression, then our extractor works with this constructor, or they conspire to allow us to take it apart, right? So it constructs and we can destruct, we can get what we want. So if we ask for the rater part of this app expression, what are we gonna get? Well, we're gonna get this, right? Lambda calculus expression, and which is it's gonna look like this, okay? That's still a internal representation, and then we can say if it's lambda calculus, we can say given this rater, give me let's see, lambda expression to body. Okay, give me the body of this lambda calculus expression. Well, the operator part of this lambda calculus, so it's going to give us the body of this, which is x, okay? And then x is going to be what? X is going to be a variable expression, and which is represented by the symbol itself. Okay, so now with those interface procedures, we can it gives us this abstraction, right? So our occurs free actually works on this, is based on this abstraction, right? There's no constructors, only extractors and predicates, because we're not building lambda calculus expression. We're just taking a lambda calculus expression in that representation in terms of the interface, and we try to judge whether a variable occurs free in this expression or not, right? So let's do a few tests, and okay, so this should return true because y is not in the variable expression. So it's not in it at all, so it's not free, and then it's a kind of not applicable case, right? So if y is part of the valid lambda calculus expression constructed using this, then it's definitely free because it's just itself, right? It's not bound to any variable or parameter, formal parameters, right, defined using lambda. Okay, so let's look at this. So this returns false because y is defined as a bound variable in the lambda expression, which is a valid lambda calculus expression. So this is definitely not free. Okay, so you can go review the logic and follow this. So this just works in the same way, right? So the only difference is now our code is a lot easier to read because we have this interface, right? Instead of relying on the current curler, the native construct we have from scheme, now we have abstraction, this interface. So this may be a little hard to understand, but this is something we're gonna do again and again in the rest of the material. Okay, we'll stop right here, check this out, and try those examples yourself.